Hello, and today we are going to go through the AQA GCSE Chemistry Paper 2 from June 2019. So hopefully you've had a really good go at the questions that you were set. So we start with hydrocarbons. So this question is about crude oil and hydrocarbons. So we have here a fractioning column, which you should be very familiar with by now. Crude oil entering a furnace, and then our different fractions coming out of our fractioning column. We also have a table which gives information about these fractions, and it's the range of boiling points that we have. So question 1, suggest a suitable temperature for the furnace in figure 1. So this is the furnace here, and we need a suitable temperature. So if we have a look at our table, we need to make sure that all of our crude oil has become a gas within the furnace. So the boiling point needs to be at the highest end. So if we have a look at bitumen, bitumen has got our highest boiling point of 450 degrees C. So that means that the furnace needs to be hot enough so that even bitumen is a gas. So our suitable temperature for the furnace should be 450 degrees C. Now, it will allow a range between 400 and 500. So you may feel that actually you want to go above 450, and that's fine. You wouldn't want to go below 400 because then bitumen wouldn't become a gas. So it has to be at least 400 to meet the lower range of your bitumen, and anything up to 500. Anything over 500 would be unnecessary. So 450 would probably be the ideal one, but anything between 400 and 500. 1.2, explain why diesel oil collects above heavy fuel oil but below kerosene in the fractioning column. Use table 1. So they want you to use the table. It's worth 2 marks, and they are asking 2 things. They want to know why diesel oil is above heavy fuel and below kerosene. So answer it in 2 parts. Why is the diesel oil above heavy fuel? Well, diesel oil is above heavy fuel because it has a lower boiling point than heavy fuel. So diesel oil has a lower boiling point than heavy fuel. So that's why it collects above. And then for kerosene, diesel oil has a higher boiling point than kerosene, so it collects below. So diesel oil has a higher boiling point than kerosene, which is why it collects below. So that's all you have to do. Suggest 2 reasons why bitumen is not used as a fuel. Now, for this, you need to remember the features of the different fractions and how the properties change as you go down the fractioning column. So if you remember, as you go down the column, the viscosity increases, the flammability decreases, and the volatility also decreases. So bitumen being right at the bottom, the reasons why you would not use that as a fuel is your bitumen would be too viscous, it's too thick, can't really do anything with it, and the flammability is too low. Okay, it's harder to ignite. So as a fuel, that would not be very useful. So that's why it wouldn't be as a fuel. You could also talk about it being not very volatile as well. That's another option that you can have. Next question. Petrol contains mainly alkanes. Which of the following compounds is an alkane? Now, if like me, you've looked at that and gone, oh, I know there's a difference between alkanes and alkenes, but I can't remember what, then have a jot down of the general formula, which you should all know. Now, even if you can't remember which one's which, it can still be useful in this question. So I know that CnH2n is 1 and CnH2n plus 2 is 1. Now, you may not even be able to remember which one's for alkanes and which one's for alkenes, but that doesn't matter because it's got to be one of these options. So C2H2, well, that's CnH2n, because 2 and 4. C4H8, again, that's CnH2n, 4 double 4 is 8. C6H14, CnH2n would be 12, so plus 2 would be 14. And C8H16, CnH2n, because 8 is half of 16. So the only one that's different is this one here, CnH2n plus 2, which means that is the only one that can be the alkane. So therefore, C6H14 is the alkane. So that's a really good way if you cannot quite remember which one's which. Of course, if you do remember that it's CnH2n plus 2, then that will make answering that question a lot quicker. But it's just a good way of just checking yourself. 1.5. Large hydrocarbon molecules in the diesel oil fraction are cracked to produce smaller hydrocarbon molecules. Describe the conditions needed to crack hydrocarbon molecules from the diesel oil fraction. So, cracking. What are the two things we need with cracking? We're just describing, so we literally just have to say what those conditions need to be. So, when you crack, you need a high temperature. And then you may remember there are two different types of cracking, catalytic cracking or steam cracking. So my other condition is going to be one of them. So either using a catalyst or using steam. So you only need to put down one of those. It doesn't matter which. Next question, 1.6. Explain why large hydrocarbon molecules in the diesel oil fraction are cracked to produce smaller hydrocarbon molecules. So I've just kept this page here because it's the beginning of the question. It's got lots of information. I've kept it there just in case I need to refer back to it. And this might be one of those moments. So if you have a look, diesel oil is fairly low down on the table. So it will be quite viscous. It will be harder to ignite. And that will give you clues to the answer to question 1.6. Explain why large hydrocarbon molecules in the diesel oil fraction are cracked to produce smaller hydrocarbon molecules. The smaller hydrocarbon molecules are more useful, and that means there is greater demand for those smaller molecules. So it's 2 marks. So we're saying explaining why, so you need to give a reason. So there is a greater demand for the smaller hydrocarbon molecules. Okay, and the reason why there's greater demand is because they are more useful, or you could talk about them being better fuels. You could also talk about the fact that you can make alkenes from them and that you can make polymers from them as well. Question 1.7. Complete the equation for the cracking of C15H32. Now, this is a great question because it is quite simply a little bit of maths. You have got part of the equation here. We just need to figure out what's left. So we're going from C15, C12. So 12 carbons have already been used here. So how many have I got left? I've got 3. And then my H's, I've gone from 32 to 26. So how many have I got left? I've got 6 left. So C3H6. And that's question 1. Question 2. Here I've got a question about lithium carbonate. Lithium carbonate is used in medicines, and here is a tablet containing lithium carbonate. Lithium carbonate contains lithium ions and carbonate ions. A student tested the tablet for lithium ions and for carbonate ions. The student used a metal wire, dilute hydrochloric acid and lime water. Plan an investigation to show the presence of lithium ions and of carbonate ions in the tablet. You should include the results of the tests. Okay, it's a 6-mark question, so we need to have a little think about what we're going to write before we start writing it. Have a look at the equipment that is being used. A metal wire, dilute hydrochloric acid and lime water. Now think about what we're testing for. Which one of these will match the test for each of these? So metal wire, we should know, is for flame tests. And out of these two, which one am I going to use for a flame test? It's going to be the lithium ions. Hydrochloric acid and lime water, I'm going to use for my carbonates. Okay, I'm going to use it for my carbonate ions because I know that carbonate has got carbon and has got oxygen. So therefore I can use my lime water as a test for the presence of the carbon dioxide that will be present. So now that I know what tests I'm going to do for each ion, I can start writing out my plan. Now, it is planning and investigation, so I'm not just going to go straight in and say, do a flame test on lithium, do a carbonate test on carbonates. It doesn't give me enough. That's not a method. It's not an investigation. I've been given this tablet, so I need to do something to the tablet in order to show that there are lithium and carbonate ions. So, first step would be crushing the tablet. Or I might dissolve it in water, and that will make it immediately more usable. Now let's go for my flame test first, just because it's first on my list. So my second stage would be to do something to my wire. I've got to make sure that my wire is clean so that there are no contaminants. So I might clean the wire. Once I've cleaned my wire, I can then put my sample on it. So clean wire and put crushed tablet onto wire, or dip into sample. And then I can talk about what I need to do for a flame test. So I need to place it into a flame. Think about the type of flame you're going to use. So I need a roaring blue flame, because you would not use a safety flame for this. You wouldn't be able to get any colour. And what should happen in that flame? There should be a colour observed. So observe the colour. If lithium is present, it will go red. Okay, so that is one of those things that you just need to learn. You need to learn the colours of the flames, actually even better than red would be crimson. Okay, crimson flame for lithium. Not finished yet. So I now need to do my test for carbonate. So step 5, I need to take crushed tablet. Don't forget about what you've been given. So I need to do something with the acid. So place into the acid. Think about what you should see when you put that carbonate into the acid. There should be fizzing or effervescence. If you know that your spelling is not very strong, then fizzing would be absolutely fine. That fizzing, of course, is a gas. And that gas, we would guess, to be carbon dioxide because it's a carbonate ion. And we can test that with our lime water. So we need to say bubble the gas, then through the lime water. And we need to say what the result of that will be. Carbonate, then lime water goes cloudy. Okay, so I've talked about how to get results for both ions. I've clearly gone through the method for a flame test. I've clearly gone through the method for my carbonate test. I've given my results of a positive flame test and results of a positive carbonate test. So I should get all of my 6 marks. It has a valid outcome and my steps are nice and logical. The tablet also contains other substances. The substances in tablets are present in fixed amounts. What name is given to a mixture like tablets? So a tablet is a mixture of substances that have specified, thought about amounts. Therefore, it is a formulation. The tablet has a mass of 1.2 grams and contains 700 milligrams of lithium carbonate. Calculate the percentage by mass of lithium carbonate in this tablet. So the tablet itself is 1.2 grams. Lithium carbonate is 700 milligrams. So it's a simple percentage. What is this as a percentage of this? Now, key thing here is our units are different. Okay, so we cannot just go straight in with immediately finding out what 700 is as a percentage of 1.2 because the units are not the same. So I need to change either one. Now, it doesn't matter which one you choose. Okay, I could put them both into grams, in which case I would have 1.20 grams for my tablet and 0.70 grams for my lithium carbonate. Or I can put them both into milligrams. So if I put them both into milligrams, I would have 1,200 milligrams and 700 milligrams. Okay, now you can do either one. Okay, you don't have to do both, as long as you've changed the unit to whichever one you'd feel more comfortable doing. Once you've got to that stage, then you can just do your simple percentage calculation. What is the percentage of lithium carbonate as a percentage of my total mass? So total mass always goes at the bottom. So I'm going to go for this one, I think. So 0.70 divided by 1.2 and then times 100 to make that a percentage. So 0.7 divided by 1.2, and that will give me 0.583 times by 100, and I have 58.3 recurring, but I'm just going to put it to 3 significant figures. Now it hasn't specified significant figures, so it doesn't matter, you don't have to put it to 3, but because 3 significant figures have been used in the question, I'm going to keep it the same. So 3 significant figures here, so I'm also going to use 3 significant figures. So that is question 2. The blank page, and remove it. Question 3 is about rate of reaction. A student investigated the rate of reaction between magnesium and dilute hydrochloric acid. The equation for the reaction is given to you. Which state symbol in the equation for the reaction does not represent one of the 3 states of matter? So states of matter are solid, liquid and gas, so S, L and G. So from here, which state symbol is not one of them? It's AQ. That's it, nice and easy. The student determined the rate of production of hydrogen gas. What 2 pieces of measuring apparatus could the student use to find the rate of production of hydrogen gas? So we've got 2 things here. We're collecting a gas, so we need something that can collect a gas. And we've got the rate. Anything that's to do with the rate of something, how quick something is going to need to be timed. So we need something that is going to be able to time it. So what can I use to collect gas? A gas syringe is going to be my best piece of equipment for collecting gas. You could also talk about maybe having a measuring cylinder in a water trough. That is another method, but a gas syringe is really your go-to here. And what do I use to measure the time? I would use a stopwatch or a stop clock or a timer or a clock or a watch, anything that can tell the time. Table 2 shows the results of the investigation. So I've got my time in seconds and I've got my rate of production of gas in centimetres cubed per second. Oh, love these questions. Plot the data from table 2 onto figure 3. You should draw a line of best fit. And they have already drawn out the axes for you and put the scale on. This question could not be any easier. So make sure you've got a pencil, please, for your assessments and a ruler, because that helps you with plotting. So my time in seconds, my first one is 10 seconds. I have 6.9. So find 10. Pop your ruler up because that always helps you keep your space. 6.9. Now I'm going up in, so every big square is worth 2. So every sort of smaller one is worth 1. So 6.9. I'm going 6.2, 4, 6, 8, 10. So I'm going to be in the middle of this square here. Okay, so I've been very specific. I know I have to be in the middle because it's 6.9. So each tiny square is worth 0.2. So I'm right in the middle and I'm on 10. Do that for the next one. So 20 is 3.9. So 3 is here. 3.2, 4, 6, 8. So 9 is going to be halfway through. 30 is 2. Lovely, easy one. 40 is 0.9. So again, so that's going to be 1. So 0.9 is going to be here. 50 is 0.3. So 0.2, 0.4. So it's going to be right in the middle. And then 60 is 0 right at the bottom. So I have plotted my data. I should now draw a line of best fit. Now remember, a line of best fit is either going to be a straight line or a curved line, and it can curve in any way. Now I can see here, I've quite clearly got a curved line. So I'm going to draw my curve. And you kind of just have to go for these. Never sure which way to go best. Let's go this way. one lovely clear curve like so. Okay, I've drawn one line. I haven't sketched it. I've done it all in one go. I've gone through all of my points. Okay, that is a line of best fit. It best fits that pattern. 3.4, give 3 conclusions that can be drawn about the rate of reaction between magnesium and dilute hydrochloric acid in this investigation. Use data from figure 3 and table 2. So it wants you to use information from the table and your graph. And it's 3 conclusions. So what does that information tell us? Well, quite clearly, I can see that the rate is decreasing. Okay, the rate of production as we go through is going down. So nice and easy, the rate decreases. The most obvious thing about that, it goes down. Another thing that I can quite easily see is that the rate becomes 0 at 60. Okay, so at 60 seconds, my rate is 0. Okay, it has stopped. Okay, one more thing that I need to conclude about this. Now, any curved line shows that there is a change in rate. Okay, if it was just decreasing at a steady speed, then it would be a straight line, but we've got a curved decreasing line. And what that means is that as time goes on, the rate of decrease is getting slower and slower each time. Okay, because my gradient is getting shallower and shallower each time. So my rate of decrease is slower. So it decreases fast here, but it decreases slowly here. And that would be my 3rd conclusion. So my rate of decrease gets slower over time. Okay, or words to that effect. So if you said it decreases faster at the beginning than towards the end, that would be fine. That would give you that mark. Okay. Question 3.5. The student repeated the investigation using dilute hydrochloric acid at a higher temperature. All the other variables were kept the same. So the only thing we've actually changed here is my higher temperature, because I was using dilute before. So all other variables were kept the same. Which 2 statements are correct? So I've got tick boxes here. 2 of them are right and the rest are wrong. So I need to decide which ones are going to be right. So higher temperature. So if you think higher temperature, things are going to happen faster. So we're looking at things where things might be getting faster because they've got more energy. So more bubbles being produced in the first 10 seconds. That does sound like something that would happen at a higher temperature. So I'm just going to put a little tick there whilst I check through my others. The activation energy for the reaction was higher. Now, the activation energy in a reaction is always going to be the same for that particular reaction. So hydrochloric acid and magnesium will have a particular activation energy. Increasing the temperature doesn't change the activation energy. It just means that I might reach it more often. So I've not changed the activation energy, so it cannot be that one. The magnesium being used up more quickly, with looking at things that happen faster, so that looks like one that it could be. The reaction finished at the same time. Now, if things are happening a lot faster, then it's very unlikely that it's going to take the same amount of time. It's going to probably finish a lot quicker. So I don't think it's going to be that one. The total volume of gas collected was greater. Now, I've not changed my quantity of hydrochloric acid and I've not changed my quantity of magnesium. So the amount of available particles hasn't actually changed. So therefore I can't make any more or any less product than I did before. So my total volume of gas isn't going to be greater. It's got to be the same. So that has left me with two options, both of them to do with getting faster. So I'm happy and confident that those two are correct. So that is question 3. Now I've asked you to skip out question 4 because we are not we're not going to look at that topic. It's not going to be in your assessments. So let's go on with question 5. This question is about combustion of fuels. Some central heating boilers use wood as a fuel. Suggest 2 reasons why the wood is more sustainable than natural gas as a fuel for central heating boilers. So we are comparing wood and natural gas. And why is wood more sustainable? So you need to be thinking about the sort of positive things about wood. Being sustainable is to do with lasting longer. So that you should start thinking, why does wood last longer than natural gas? So wood, we know, is renewable, whereas natural gas is finite. So that would be one reason why wood is more sustainable. What else do we know about wood? So we know obviously that wood comes from trees. It comes from a plant. Whereas natural gas is a fossil fuel. So the big difference there is to do with carbon dioxide. So wood produces the same amount of CO2 when burned as it absorbed over its life. So as that tree grew and took in carbon dioxide from photosynthesis, it's only got that much carbon in it to release when it's burned. So it makes it carbon neutral. So that is more sustainable because we know that natural gas takes many, many years to form, thousands and thousands of years to form, so therefore is not sustainable. Natural gas is mainly methane. When methane burns, it can produce both carbon monoxide and carbon dioxide. Explain the process by which carbon monoxide can be produced when methane is burned. So we're only now interested in how we get carbon monoxide. Now we should know that carbon monoxide is a product of incomplete combustion, whereas carbon dioxide is a product of complete combustion. And the difference between complete and incomplete is the amount of oxygen available, which is why carbon dioxide has 2 oxygens, carbon monoxide has 1, because there's not enough available. So that gives us our 2 answers. So there is not enough oxygen present, and that is incomplete combustion. Okay, so use these key terms within your answers. It's the oxygen that is key here because that's the difference between monoxide and carbon dioxide. 5.3, balance the equation for the combustion of methane to produce carbon monoxide. So balancing equations, have a look at what you've got on each side. So I've got 1 carbon, I've got 4 hydrogens, I've got 2 oxygens, and this side I've got 1 carbon, 2 oxygens, but only 2 hydrogens. Okay, so I need to start thinking about how I can increase it. Always good to use a pencil, I think, for this, because then it's quite easy to change things if you need to. At the moment, I need to change my number of hydrogens. I need to double this, so I could put a 2 here. That would make that 4. that would also change my number of oxygens to 3. Whereas I've only got 2 over here. Now a 3 and a 2 is always an interesting combination. Okay, what I need to do if I've got a 3 of one thing and a 2 of the other on the other side is think about what they both go into, which in this case would be 6. So 2 oxygens here. To make that 6, I would need to make that 3. So I've got 6 oxygens altogether. That is obviously going to change what's happening over here. Now, whatever I change here, obviously I've got this oxygen to think about as well. So if I changed, I've still got 1 carbon. Now if I change this again, if I change this to 4 to make 4 oxygens, and I change that to 2, that would give me my 6. But now I've got 2 carbons here, and I've got 8 hydrogens there, but that will work because if I've got 2 carbons here, I need 2 carbons here, and therefore I've also got 8 hydrogens here. And I think I'm balanced. 2 carbons, 8 hydrogens, and 6 oxygens. Yes. So being happy with that, I can say I've got 2, 3, 2, and 4. So that's why it's good to use pencils, so you can then rub it out and make it really clear, obvious afterwards. Quite a tricky one, that, but wouldn't take you too long to work out. 5.4. Propane burns in to form carbon dioxide and water. The equation for the reaction is C3H8 plus 5O2 goes to 3CO2 plus 4H2O. 3.6 decimeters cubed of carbon dioxide is produced when a sample of propane is burned in 7.25 decimeters cubed of oxygen. Calculate the volume of unreacted oxygen and give your answer in centimeters cubed. So basically I've used 7.25 of oxygen, not necessarily what I needed to use because I've got some left over. Okay, but I know that using that oxygen, I have produced 3.6 decimeters cubed of carbon dioxide. So I always like to start these questions by rewriting out my equation, just because I like to have that little bit more space. So I used 7.25, although I didn't need all of that. And I made 3.60. So this really is my starting point because I know that that used a specific amount of oxygen, whereas 7.25 I know isn't actually what I needed to use. So I need to work out what I needed in order to work out what was left over. Okay. So I'm going to use this equation. Okay, so moles is volume divided by 24. So let's use that to find out how many moles of CO2 I have, and then I can use that to work out how many moles of oxygen I have, and then I can use that to work out what my volume should have been. So 3.60 is my volume. That goes on the top. Divide that by 24 because I'm working out my number of moles. If you do that in your calculator, you should get, that will give me 0.15. Okay, now 0.15 would be 1 mole. So I've got 3 to 5, like as a ratio. So what I need to do is work out how many moles of oxygen I needed. So if I do 0.5, if I divide that by 3, that will give me 1 mole, because this is 3 moles. So divide it by 3 will give me 1 mole, and then times it by 5, I can see how many moles of oxygen, because I've got 5 here, and that will give me 0.25. So I've now got 0.25 moles for oxygen. I can use that to work out what volume of oxygen I actually needed. So 0.25, we're now working out volume. 0.25 times by 24 gives me 6. So I actually needed 6 decimeters cubed of oxygen, but I used 7.25. So my unreacted oxygen is just going to be the difference between that. So 7.25 minus 6. 7.25 minus 6 is going to give me 1.25 decimeters cubed. Okay, now I'm not quite at the end yet. When you get to this point, it's always good just to double check through. So I've gone through that bit, I've calculated my volume. Give your answer in centimeters cubed. I'm in decimeters cubed at the moment. So if I want to go from decimeters cubed to centimeters cubed, I need to times by 1,000. So 1.25 times 1,000. Not that you should need to do that in your calculator, but that will give you 1,250 centimeters cubed. Okay, there are other ways of doing this. Okay, I like to use that equation and work out the moles. You may have your own way. Okay, but if maths isn't quite your strong point, then try and remember using volume is moles times 24. If we weren't using gases and we were using masses, then you would use mass over moles times molar mass. Okay, so if you were using masses and solids, you would use that one instead. Okay, question 7, because we've missed out question 6, because again, we're not actually doing that topic in our assessments. A large amount of aluminium sulfate was accidentally added to the drinking water supply at a water treatment works. Describe a test to show that the drinking water contained aluminium ions. Give the result of the test. So, aluminium ions, the test for that is adding sodium hydroxide. Okay, so we need to add sodium hydroxide. Okay, that's us describing the test. The result will be a white precipitate. However, we are 3 marks. Okay, that will obviously only give you 2. Now, aluminium ions are not the only ions to produce a white precipitate in sodium hydroxide. Okay, you can also have magnesium ions will also give a white precipitate. However, the way to tell the difference, if you keep adding sodium hydroxide, aluminium ions will dissolve, whereas magnesium ions will not. So magnesium ions will stay as a white precipitate, but aluminium ions will eventually disappear. So white precipitate will be formed, but keep adding sodium hydroxide and it will go clear, because aluminium ions are soluble in excess sodium hydroxide. Okay, so if we add excess, if we add more sodium hydroxide, then our aluminium ions are soluble in that, and so they will disappear. Describe a test to show that the drinking water contained sulfate ions. Give the result of the test. So if you remember, when you are testing for a sulfate, you need to add barium chloride and hydrochloric acid. Okay, we've got 2 things that we need to add. And my result is a white precipitate. Okay, So make sure you remember the test for aluminium ions, the test for sulfate ions. 7.3. Plan an investigation, again, to find the total mass of dissolved solids in a 100 centimeters cubed sample of drinking water. Your investigation should produce valid results. So we know that we have solids that have been dissolved in 100 centimeters cubed of water. We need to find the mass of those solids. So what do we need to do? We need to weigh our solids from 100 centimeters cubed sample. To do that, we are going to have to obviously get rid of the water. Best way to get rid of the water is to evaporate it. Okay, so this is sort of leading us into how we're going to do this investigation. So we need to, if I just think about it, we need to evaporate water. We need to weigh solids accurately, thinking about what I'm going to put it in, that don't have to do lots of transferring. So I'm probably going to use an evaporating dish because that's the best thing to evaporate in. Be best to weigh my evaporating dish beforehand, so then I don't have to like tip out the contents, and that makes it a bit more accurate. So let's go with that. So the first thing I'm going to do is I need to weigh an evaporating dish. Okay, so I know what the weight of that, the mass of that is. I need to add in the measured volume of water. So you don't have to use the whole 100 centimeters cubed sample. I could use a sample of the sample and still work out the total mass. So let's say I use 10 centimeters cubed, whatever I get at the end, I just times by 10. So add in a measured volume of water, whatever that could be. So let's say 10 centimeters cubed. Then I'm going to heat it. So heat to evaporate the water, because that's what I need to do. I need to get rid of the water. So heat to evaporate the water. When I think the water's gone, I'm going to weigh it. Now I say when I think the water's gone, because actually after weighing it, it would be sensible to heat it again, just in case there is still some water present. So weigh it, reheat, and then weigh again. And basically you want to keep doing that until your weight doesn't change anymore, your mass doesn't change, and that will prove that all the water's gone. So you would say just repeat 5 and 6 until mass is constant. So then you can be very sure that you have gotten rid of all of your water. So then you've got your mass, but also we need to take away our evaporating dish mass. So subtract mass of evaporating dish from final mass. We want to produce valid results, so you could repeat everything. Repeat the whole experiment 2 more times to calculate the mean. Okay, that helps you get valid results if you're calculating a mean, because you can remove anything that's anomalous. And then whatever you get as your end result, if you need to times that by 10, then you'll need to say that, okay? So if 10 centimeters cubed of water was used, then multiply by 10 to get mass in 100. Okay, so it's just being clear that if you only use 10, then also you need to times it by 10 at the end, because it's the mass in 100 centimeters cubed. And that's it. So it's quite a simple experiment, but actually you need to really think about those steps of what you need to do. And it's the valid results that are key here. So it has to be valid. You have to make sure that all that water's gone. Repeating it and taking a mean will help it to be valid. So just think about what valid means and how your investigation can be valid. Okay, question 8. Titan is a moon of the planet Saturn. Table 3 shows the percentages of the gases in the atmosphere of Titan. We've got nitrogen 98.4%, methane 1.4%, and other gases 0.2%. Some scientists think that living organisms could have evolved on Titan. Explain why these organisms could not have evolved in the same way that life is thought to have evolved on Earth, and use Table 3. So what is the key thing that we are missing here that we have on Earth that led to the evolution of life? Well, it's basically oxygen, isn't it? So there is no oxygen here, whereas on Earth, in order for animals to be produced, we needed to have that oxygen, and that came from plants. So that is starting to lead us into the right direction for our answer. So let's use the obvious. There is no oxygen present. So if there's no oxygen present, that means that there hasn't been any photosynthesis happening. So there's no photosynthesizing organisms on Titan. There's also no carbon dioxide present. So that's another thing that you could mention. So we've got no oxygen present on Titan. So there's no photosynthesizing organisms to release that oxygen. There's also no carbon dioxide present for them to start photosynthesizing with in the first place. So basically all that leads to is there are no animals that use oxygen on Titan. Okay, so it's 3 marks. We've said 4 different things. Saturn has other moons. The other moons of Saturn have no atmosphere. Titan is warmer than the other moons of Saturn because its atmosphere contains the greenhouse gas methane. Explain how this greenhouse gas keeps Titan warmer than the other moons of Saturn. So we're basically saying, why does methane act as a greenhouse gas? How does it keep the planet warm? So think about the greenhouse effect. The greenhouse effect on Earth will be the same as the greenhouse effect on Titan. Okay, if we've both got greenhouse gases in the atmosphere, it will work in exactly the same way. So don't let the fact that it's somewhere else in a different planet or a different moon affect the answer. It's the process is still going to be exactly the same. So we're explaining, so we need to say how the greenhouse gas keeps it warm. So think about the different stages of the greenhouse effect. We've got shorter wavelengths, radiation passing through the atmosphere from the sun. So it allows those short wavelengths in. The surface of the moon or the planet will re-emit them as longer wavelengths, just like they do on Earth. So they are re-emitted from the surface as longer wavelengths. So we're basically moving from the infrared, from the visible light to the infrared spectrum. Those longer wavelengths are then trapped or absorbed by the methane. So the longer wavelengths are absorbed or trapped by the methane, and then that is what obviously keeps it within the Earth. Okay, it's exactly the same as on Earth. Shorter wavelengths can pass through, surface re-emits it as longer wavelengths, and the greenhouse gases absorb that, so it keeps the heat in. It's the same thing happening, it's just on a different, it's on a moon rather than a planet. The atmosphere of Titan contains a small amount of propene, hydrocarbons. Describe a test to show that propene is an unsaturated hydrocarbon. So, completely different topic from chemistry, but they've chucked it in here, which is fine. So, an unsaturated hydrocarbon, what is the test for that? The test is add bromine, water. Remember, bromine is that kind of browny coloured liquid. And if it's unsaturated, then it will turn to colourless. So it will go from orange or brown to colourless. Okay, colourless is key. It's not clear. It doesn't go clear. It goes colourless. Okay, because you can have coloured clear liquids. So it's a colourless liquid. That's the important part there. Okay, question 9. Some students investigated the rate of decomposition of hydrogen peroxide, H2O2. This is the equation. The catalyst is manganese dioxide. Describe a test to identify the gas produced in this reaction. So our gas is oxygen. What is the test for oxygen? We need a glowing splint to test for oxygen. And what is the result? It will relight. Nice and simple. Student A investigated the effect of the particle size of manganese dioxide on the rate of reaction. So we're looking here, surface area and rate of reaction. This is a method used. Measure 25 centimetres cubed of 0.3 mole hydrogen peroxide solution into a conical flask. Add a spatula of manganese dioxide powder to the conical flask. Measure the volume of gas produced every minute for 10 minutes. Then repeat steps 1 to 3 with coarse manganese dioxide lumps. The method student A used did not give valid results. What 2 improvements could student A make to make the method give valid results? So we've got 2 boxes to tick. So we need to go through these, decide whether it makes it more valid or not. So measure the increase in mass of the conical flask and the contents. Is that going to help this reaction? Is that going to help make this more valid if I measure the mass increase instead of the gas being released? Well, no, not really, because it's not going to increase mass because I'm producing a gas which is going to escape. So it can't be that one because the mass isn't going to increase. Measure the volume of gas produced every 2 minutes. So I'm doing every minute. If you did it every 2 minutes, then you've got a larger gap between measurements. That's not going to make it more valid. That's going to make it worse. So it can't be that, because the more measurements you take, the more valid your results are. Place the conical flask in a water bath at a constant temperature. Is that going to help me control my my experiment? Is that going to make it valid that nothing else is affecting it? Well, yeah, it is, because it's going to make sure everything's at the same temperature. Remember, valid is a little bit like making things it's all about looking at the controls, and are we keeping everything else controlled, which we are. Using 0.05 mole decimeters cubed of hydrogen peroxide. Well, that's just changing the concentration. That won't make it more valid. That just is testing at a different concentration. Use a mass of 1 gram manganese dioxide each time. So what were we doing before? Adding a spatula. Well, yeah, I mean, that's going to help, isn't it? Because using a spatula, I don't really know how much I'm putting in. A spatula of manganese powder and a spatula of coarse manganese is going to be massively different. So actually, yeah, using a gram, if I'm making sure my mass is the same, then it's only the surface area that I am changing. So it's got to be that one, and it's got to be that one. Okay, student B used a method which gave valid results, thank goodness. Figure 9 shows B's results. So we've got our fine manganese dioxide powder, and we've got our coarse manganese dioxide powder. Determine the mean rate of reaction in centimetres cubed between 2 and 4 minutes for coarse manganese dioxide lumps. Give your answer to 2 significant figures. Okay, so I'm going from 2 and I'm going to 4. So at 2, I've got coarse, 2 to 4, 2 significant figures. So read up from 2. You can use a ruler if that makes things easier. So if you read up from 2, my volume of gas at 4 minutes. So I've got 42, 44, so 45 there, and 52, 54, 56 there. So I've gone from 45 to 56, 45 to 56. So the difference there, 6 minus 45 is 11. So my volume of gas change is 11 centimetres cubed. And 2 to 4 minutes. Now, we're centimetres cubed per second, so minutes isn't going to help me. 2 minutes is 120 seconds. Okay, so that's my amount, my length of time. So I've produced 11 centimetres cubed in 120 seconds. So all I have to do is my volume of gas produced divided by my time. 11 divided by 120, 0.0916. Remember, it's 2 significant figures. So that is going to be 0.092 to 2 significant figures. .4. Hydrogen peroxide molecules must collide with manganese dioxide particles for catalysis to take place. Student B repeated the experiment with coarse lumps of manganese dioxide. They used the same volume of 0.2 mole decimeters cubed hydrogen peroxide instead of 0.3 moles per decimeters cubed of hydrogen peroxide. So we've got a lower concentration. Sketch on figure 9 the curve you would expect to see. Assume that the reaction is complete after 9 minutes. Okay, so it's the coarse lumps still. So I'm still using coarse lumps. So I'm really looking at my black line here, but I'm using coarse lumps with a lower concentration. If I've got a lower concentration, where am I going to see it at the end? So assume that reaction complete after 9 minutes. Lower concentration being used. So I need to have a line that starts at the, obviously starts at the origin. It's going to be less steep than my solid line. So I've got to go underneath my solid line. Like so. And it's going to end after 9 minutes. Now, because I'm using a lower concentration, I've got less reactant particles. So I'm actually going to produce a lower volume of gas because I've got less particles reacting. Okay, so my line starts at my origin, is lower than my original line, and I'm going to produce less gas because I've got a lower concentration. (9.5) The rate of reaction is different when manganese dioxide is used as a fine powder rather than coarse lumps. Explain why. You should answer in terms of collision theory. So they very clearly said that they want you to talk about collisions within this. So why is a fine powder different to coarse lumps? So what they haven't actually mentioned at all is surface area. So it's the first thing you're going to talk about. The surface area of powder is more than the lumps. Okay, so sort of state that obvious fact first to get your first mark, and then you need to explain that in collision theory. So why is being a powder, why does that mean that the rate of reaction is different? So with the powder, we'll have more collisions per whatever unit of time than the coarse lumps. Okay, so we're talking about having more collisions or more frequent collisions, so they will collide more often. Okay, question 10. We are at the last bit now. This question is about reversible reactions and equilibrium. Hydrogen is used to produce ammonia in the Haber process. The hydrogen is made in 2 stages. Stage 1 is the reaction of methane and steam to produce carbon monoxide and hydrogen. The equation is shown. It's reversible, so we've got our little reversible symbol there. Calculate the atom economy for the formation of hydrogen in stage 1. Okay, so atom economy. We are forming hydrogen. So how many atoms have I got here? Obviously I have got 2 relative atomic mass of hydrogen is 1, so 3H2. I've got 2 there times 3, that will be 6. And then what do I start with? My atom economy formation of hydrogen. So if I calculate this side, I've got 12 plus 4 plus 2 plus 16, and that will give me 34 altogether. So I've started with 34. I basically then want to know what 6 is as a percentage of that. So 6 divided by 34 times by 100 will give me 17.647. So let's do 17.6%. Okay, so the atom economy of this compared to what I've started with. So I've started with 34, I've got 6 hydrogen, so 6 over 34 times 100. Explain why low pressure is used in stage 1 and give your answer in terms of equilibrium. Okay, so we think about here the number of, if we're talking about pressure, we need to talk about the number of molecules we've got. So I've got CH4 plus H2O, CO2 plus 3H2. So I've got 2 on this side, and I've got 4 on this side. So I've got 1 molecule, 2 molecules, I've got 1 molecule, 3 molecules, so 2 and 4. If you increase the pressure, it's going to favour the side with less molecules. Okay, if you keep the pressure low, it's going to favour the side with more molecules. So here we're keeping the pressure low because we want to make more of our product. So therefore we need to favour having more molecules. So I want a higher yield of products. Okay, I'm trying to make more products. Products have more molecules than reactants. So low pressure favours more molecules, which is the product's reaction. Okay, so it's just making that really clear. I want to make more of my product, so therefore I need to favour that side in terms of pressure. So a low pressure is going to favour more molecules, so I'm going to favour that side. Stage 2 uses the carbon monoxide produced in stage 1. So we're now using that carbon monoxide. The carbon monoxide is reacted with more steam, so more H2O as a gas to produce carbon dioxide and more hydrogen. And again, we're given the equation. What effect of increasing the pressure on the equilibrium yield of hydrogen in stage 2? So basically they're saying if I increase the pressure again here, what's going to be the effect on the equilibrium yield? Pressure, again, is number of molecules. So I've got 2 molecules on this side and I've got 2 molecules on this side. So if I change the pressure, neither side is going to be favoured. So it's going to have no effect. So what is the effect? There is no effect because the changing pressure, the molecules are the same. So the position of equilibrium will not change. Figure 10 shows the percentage yield of ammonia produced at different temperatures and pressure on the Haber process. So we've got these different temperatures, we've got different pressures, and we've got different percentages being produced. A temperature of 450 and a pressure of 200 atmospheres are used in the Haber process. A student suggested using a temperature of 350 and a pressure of 285, should be out here, could be used instead of those used in the Haber process. Determine how many times greater the percentage yield of ammonia obtained would be. Use figure 10. Okay, so we basically start with 450 and a pressure of 200, which is here, and they're saying use 350 and 285. So let's just make sure that's definitely where we want it. So that's 250, 60, 70, 80. So it's there. Okay, so basically what is the difference between these two is what we are being asked. So let's have a look. Let's read that across there. And read that across there. So this one is 28%. And this one here is 63%. Okay, so I've got 63 to 28. How many times bigger is 63 to 28? Well, that's very easy to do. 63 divided by 28. Definitely need a new calculator here. Make sure your calculators are working for your assessments. Come on. Oh, it's there. 63 divided by 28 gives you 2.25. So it is 2.25 times greater. Okay, last few questions. a pressure of 285 atmospheres is not used in the Hydrocarbon process instead of 200. Give a reason why. Anytime you are increasing the pressure, you are increasing the danger of that process. You are increasing the cost of that process because it requires energy to get that pressure. Remember, do not mention cost without mentioning energy. So it's only 1 mark, so either of those will do. So it would increase the energy costs because you're using a higher pressure. You could say also higher pressure is more dangerous, more likely to have a risk of explosions. Okay, so they're kind of your 2 go-tos there. How does figure 10 show that the forward reaction in the Hydrocarbon press is exothermic? Okay, how does it show, how does this show that the forward reaction making ammonia is exothermic? Okay, so if the forward reaction is exothermic and you want to increase that, exothermic means releasing heat. So you need to have the conditions where you're going to release more heat. And to do that, you need to lower the temperature. So if you lower the temperature, then the forward reaction will want to happen more because more heat will then be released to try and get the temperature back up. This proves it because the highest yield is at the lower temperature. So the lower temperatures are giving you a higher yield. Okay. So that's what you need to say. So the lower temperatures give a higher yield, or you can say it the other way around. So the higher temperature gives a lower yield. And that's it. It's only 1 mark. So that's all you need to say. You can talk about, therefore, it's shifting in equilibrium, but that is basically what that proves it. World production of ammonia is now 30 times greater than it was in 1950. Why would the demand for ammonia have increased? Think about what ammonia is used for. Okay, ammonia is NH3, so we've got nitrogen in there. It is very important in fertilizer. Okay, and why would the use of fertilizer have increased from 1950? So in 1950 to now, there's a lot more people. And if there's more people, we need more food. And if we need more food, then we need to grow it. And therefore, fertilizer is going to be important in that. So there is a larger population, therefore requires more food. So more fertilizer is needed. Okay. Because the population has increased, there are lots of other things that ammonia is used in that we might need more of. So you could say explosives, although that's not really the best one to say, but ammonia is found in explosives. Things like drugs makings, dyes, nitric acid, all those sorts of things also contain ammonia as well. So just having an increased demand for something that contains ammonia due to having a larger population. But fertilizer is kind of your key one there. We need more food, so we need more fertilizer. And that is the end of the questions. I hope you did really well.